Now we have the chance to introduce Helen Maynard-Cathley, who's is a planetary scientist at the Bragg Institute at ANSTO. I had breakfast with her and her colleagues, and I learned quite a lot about what's going on there. She investigates materials relevant to the surface of the icy moons Europa and Titan, and she promotes science widely through speaking and popular writing, and is particularly interested in women in physics and the gender equity initiatives. Helen, we look forward to your talk, please.
Well, thank you very much. I realise there's a bit of a dearth of history in my talk, so I thought before I really got stuck in, I would talk about some of the inspiration that led me to become a crystallographer. And one was because as a planetary science undergraduate, I did at University College London. One of the buildings I used to go in all the time was the Catherine Lonsdale building. And so, of course, naturally brings you to Googling and seeing who was this Catherine Lonsdale and understanding a bit about her work and her impact. And that meant that when I came to a point of, now I should say as a planetary scientist, we tend to be jack of all trades but masters of none. And we generally have to pick a tool in order to go onwards and to do our science to apply to the planets. And at that point, I was thinking, wow, this mineralogy, crystallography looks pretty good and pretty tempting. And then seeing sort of the luminaries in the field being women was obviously quite a big sort of big step for me, and I was able to look and go, oh, I could do this too. So not just Catherine Lonsdale, but Helen Magor, who was the first to determine the perovskite structure, which is incredibly important, not just to earth sciences, but to mineral science, to material sciences, and could be the future of solar cells as well. So it's very, very inspiring. And I should say also, Lawrence Bragg inspires me a lot in my science communication work. Although he's accoladed, and rightfully so, for the pioneering work in crystallography, it's not always recognised how much he did to promote talking about it to the public. He became the director of the Royal Institution later on in his career, and it's probably not widely recognised. He was actually he was reportedly the first person to present a scientific TV show for children. It's called Nature of Things, and you can actually look at it on the RI channel. It's absolutely amazing. At one point, he talks about the pairing of electrons as couples doing the Highland fling. So I really do recommend that to see the great master talking about his science, but to children as well. So that's really fantastic. So that was my history. I thought I would take the opportunity to take you through a journey through the solar system, and to see where crystallography, and I should say the tagline to this presentation would be small things that can have a big impact. Where are we using tiny samples of crystallography to understand more about the biggest things in our solar system, the planets? So we have a lot of diffractometers on Earth. If any of you have collected data from diffraction machines, you're quite aware that they're quite big, quite bulky, and there's some up and down the country, all around Australia, people collecting this data. We also have two, as has been mentioned by AD earlier on, two big central facilities for doing diffraction, the Bragg Institute, where I'm currently based, and the Australian synchrotron, where I was based before. Now, the real nice things about these facilities is, especially in terms of the synchrotron, they give us a higher flux of X-rays than we can get in the laboratory. And this enables us to look at very strange conditions, much smaller samples that we put under very, very exotic conditions. And with the neutron crystallography, which is the trade that I apply these days, we can look at very different properties of materials, so such as locating where those pesky hydrogen are, which is difficult to see with X-rays, or magnetic structures in materials, just for instance. So we've started on Earth, but Earth is actually not the only planet in our solar system where we can run a crystallography experiment. As of 2012, we can now run crystallography experiments on the surface of Mars. And that's because of the Curiosity rover, which landed there. And although we're all very aware of the amazing pictures it's putting out from its even, someone pointed out to me, it was the first rover to act like a teenager. And the first thing it did when it landed on Mars was it took a selfie. Hey guys, look where I am. It's fantastic. But not just with those beautiful images, people are less aware of the small diffractometer sitting inside it. Now, again, anyone who's collected data on a diffractometer, the one I used to use at the synchrotron is about the size of a single Docker bus. How have we gone from taking a diffractometer about that size, or in the laboratory size, and being able to miniaturize it so that we can put it in a rover and send it to space? Well, that's work of over 20 years of research by the NASA Ames laboratory. And that was actually so successful that they've actually spun it out into a company, and that they can actually offer these, units, the Terra portable XRD units, available for other researchers. So here we have a picture of Terry, the Terra, who lives at Monash with Sasha Wilson. And she finds him fantastically useful. He can go out with her into the field, and she doesn't need to wonder when she picks up her samples what the minerals are. Normally, you have to wait, go back to the laboratory and analyze them. She can analyze them in the field and work out what they are. Now, that's exactly what Curiosity is doing. And there was quite a lot of technological advances to get the diffractometer to this stage that you could put it onto Mars. And one of the key ones that I thought was particularly interesting and quite engaging was that when we collect powder diffraction data, which is what Curiosity is doing, we generally have to rotate the sample a little bit. That gives us a little bit better powder averaging, basically gives us better data. Without rotating, we tend to get lumps stuck in the way and doesn't quite represent all the minerals there. So they had to find a way of rotating the sample without actually having too many moving parts. Moving parts in space are a very bad thing. They can all go wrong. And an ingenious way that they got around this is they actually based their sample holder on a tuning fork. So you can see there that the sample holders there is pretty much like a tuning fork. And in the middle there, there's a motor that can vibrate it. And that's the other really nice thing I like to think about Curiosity. Currently, it's taken, I believe, 5 diffraction patterns. And every time it takes that diffraction pattern on Mars, it sits there and hums to itself while it's doing it. So it's quite cute. But you can see the impact of being able to move around the sample like that as you get very, very beautiful data. And that is the first diffraction image that they took from the rock nest area of Mars, which is very close to where it landed. And this instantly showed you why you would send a diffractometer to Mars, because in the middle there, you can see the point where the beam stop hasn't quite got in the way of the central beam. You see a brighter area at the bottom that is the direct beam coming through. There's a nice little story about that, because if any of you are aware of how Curiosity got to the surface of Mars, it was quite a violent event. It sort of hurtled through the atmosphere of Mars, and then all of a sudden a parachute opened and it was hurtled back up, and then it was sort of gently floated back down to it got close enough, and then these big retro rockets were fired, and again it was vaulted up into the air, and then a little crane sort of just lowered it onto the surface of Mars. So not exactly the most gentle of arrivals to Mars, and so you probably can understand why the beam stop might have got dislodged. But as Dave Bish, who one of the PI investigators on the ChemMin instrument, the diffraction instrument on Curiosity, he said that, no, they were running checks on the launch pad and saw that all it was that someone knocked it when they were putting it together. He mentioned this to the people assembling the rocket and said, can we just get in there and nudge it back? And they went, nope. So they've just had to live with it. But the really nice thing is that despite that, they can still see the diffraction from clays. And that's that ring very, very close to that point there. And that's exactly why you want to send a diffractometer to Mars, is that instant payback there that we've seen clays on the surface of Mars. Not only we've seen them, we can pretty much prove that they're there. So why are clays so important on the surface of Mars? And here I'm comparing a diffraction pattern taken on Earth, actually at the Australian synchrotron, with one taken from Curiosity. In fact, it's the integration of that same diffraction pattern. And all I'm doing there is I'm using Hugo Rietveldt's logarithm, a Rietveld refinement, to fit 2 mineral phases there, a pyroxene, so the chain silicate, and a feldspar, so most of the constitutes of the crust on Earth. And you can see it fits really nicely to the Mars diffraction as well. And there's a little example, a bit more of a detail there, showing actually how nice it is. But you can see that the clay peak there, the one at the really high D-spacing, so around 8 angstroms, is not being fitted because I'm not fitting clay at that point. But that's really nice showing that the clay is there. And, but why is that so important? Well, clay needs water to form. And not only does it need water to form, it needs some sort of alteration event. So it shows that Mars has been geologically active, which we knew, but also sort of post-active. That not only have we seen volcanism happen, we've actually seen the minerals wear themselves down and go through another evolution, as it were. The other nice thing about clays, and it's the reason why clays have suddenly become very sexy science, is because that water layers that are trapped within their very, very makeup. So clays are these phyllosilicate minerals, so silicate layers with water trapped in between the layers. And that makes it quite a nice place for a bug to live. Or a little bacteria. If you were a bacteria, you'd want to live near some clay because you've got some water, if you can cling it off the silicate, and you've got some minerals there. So it's really making Mars look a less inhospitable place than we thought before. So the thing I thought was nice about the talk as I was sitting there is it actually shows a nice bridge between Professor Pring and Professor Batten, who comes later, because as we move, oh, I missed a point there. I missed the fact that the sample I took came from, the sample I'm taking there actually came from Iceland, and so the essential point there is that, and there I didn't have a Curiosity rover to go and collect that sample. I had a friend called Kate who collected bits of Iceland for me to compare to Mars there. And that's really nice, that now we have a grounding of what Martian surface is like, so Hawaii and Mars and Iceland. We can actually sort of go back and understand a little bit more. We have 100 years of study of Iceland and Hawaii, and we can use that to help us inform a little bit more about how we're going to study Mars and understand a bit more how its climate has changed and its habitability has changed. But I got ahead of myself a little bit there, and I talked about how the minerals of the solar system actually change as you move outwards. And when you get beyond the big block of Jupiter, it changes quite dramatically. Those silicates, those minerals that Professor Pring talked about, they don't become so dominant. They get sort of trapped in the interiors of these moons and the planets we think. And the surfaces are dominated by smaller molecules, principally water, but other sort of hydrocarbons and aromatic materials. And we have, and this is my sort of thing that gets me out of bed every morning, is the study of these icy moons. We have a beautiful suite of icy moons, I should say, with the exception of Io, who's actually quite silicate-like, that live out there. And they are tremendously varied. There's all sorts of chemistry and happening on their surfaces. And not just chemistry that we detect, but also geological features that we can compare back to Earth as well. But we don't have a diffractometer on these moons yet, I hope. And so how do we actually go about understanding anything about their surfaces? So we'll zoom into Europa, and we'll use Europa as a bit of an example. And I've pulled this out of the archives, which I thought was really nice. So this is the Galileo spacecraft, which is the reason we know pretty much anything about the icy moons of Europa and Ganymede, which live around Jupiter. And it met a sort of fiery end into Jupiter in around 2004, I believe. But before it got there, it sort of had to slingshot around the Earth. And it used one of its spectrometers to take an image of Australia as it went by. And this image is taken from 50,000 kilometers. And it's false-colored image, but one thing that's really, really nice about this is you can see, and this is just analyzing the reflected light from the sun, you can see where the Great Barrier Reef is. From 50,000 kilometers, you can see that very different colored area there, showing a different range of minerals just below the surface of the water. So at 50,000 kilometers, you can take those details. Galileo went as close as 180 kilometers to the surface of Europa. And with that same instrument, was able to map great swathes of both Europa and its sister moons, Ganymede and Callisto. And it pulled out all this spectroscopy. So this in particular is the near-IR spectrometry. And The really nice thing is this is sort of the process of how I sort of justify doing my research. Is you take the NASA data, the Galileo data, which is that dotted line there, which is the data as measured by NIMS. And then you can fit to it laboratory measured spectra of hydrates and materials that we guess are there. One of the big puzzles about Europa is we know there's water there. We're pretty set about that. But there's actually a significant amount of something else. Jury's still out as to what that something else is. But one potential thing is its sulfuric acid hydrates. And that's driven, the process of these hydrates developing is actually driven from Io, which has great big sulfur volcanoes that put out ionized sulfur into the Jupiter area. And these sulfur ions actually hit onto the surface of Europa and convert to sulfuric acid hydrates. That's the hypothesis. And so I sort of started thinking, well, do we know enough about the crystallography, actually what these materials are? You know, if I prod it, what does it do? And so the very simple start of this whole investigation was going into the lab at the synchrotron and grabbing out a bottle of sulfuric acid and a bottle of water, mixing it and freezing it at European conditions down to around 120 Kelvin. It was nice there that I got a diffraction pattern of a material that was known, an octahydrate, and that's the main peak there. But you can see on that pattern there's a load of stars. And those stars indicate peaks from a material that we didn't know. And that's a new hydrate. It's a sulfuric acid hexahydrate. And then I went on to solve the crystal structure a bit later. The nice thing about the sulfuric acid, or the acid hydrates as they're now being coined by NASA, is they're actually quite layered materials. And in a way, they're analogous to the clays of the icy moons. And that actually that sort of layeredness will probably dominate their physical properties. We've already seen that it dominates their thermal properties, but it could also dominate their strength. And so that gives a potential weakness in a way that things like this very, very interesting and chaotic terrain that we see on Europa could actually form. So Europa's all very well, but I thought as I was here, I would take the opportunity to talk about another icy moon and a slightly more recent study I've been involved in. So Titan is the subject of a very ongoing exploration by the Cassini spacecraft, which is still there and has luckily had its mission extended into 2017, where at the end of 2017 it will also meet a bit of a fiery doom into the center of Saturn. And the main reason is again, it's powered by a small nuclear reactor, and they don't want to get anywhere near Titan. They want to preserve Titan. And Titan's been shown to be incredibly Earth-like. It has an atmosphere. It's something that was noted by Gerald Kuiper back in, I think it was 1944, who wrote that paper. And not only does it have an atmosphere, its surface pressure at the surface of Titan is around 1 bar. So it's around the same pressure as the surface of Earth. And also, it's a nitrogen-rich atmosphere, but they also noticed that there was methane there, which puzzled them quite a lot at the time. Now, Cassini was a little bit more difficult to take spectrometry from the surface of Titan because it has these very hazy clouds. And so they've used radar in order, like they've done for the surface of Venus, to pick out its surface. And again, you can start comparing features on the surface of Titan with those on Earth. And one of the biggest discoveries that Cassini has made, and in my opinion, one of the biggest discoveries made in the last few years, is the fact that we have standing bodies of liquid on the surface of Titan. And not only do we have these standing body of liquids, but we also seem to have these bright patches of potential evaporites. Now, I say they're liquid, and the thing I should caution you about is that it's now revealed by Cassini that there is a hydrological cycle, that not only do you have the liquids, you have clouds, you have the cycle going around. But it's a hydrological cycle where water plays a very small role, in fact, none at all. It's a hydrological cycle dominated by methane, very small hydrocarbon molecules. So those lakes are thought to be mainly composed of methane and ethane, and that evaporates and we get clouds coming through. And we understand quite a lot of the structures involved in this. We understand the methane clathrates, which capture methane perhaps in the crust. We understand a bit about ammonia hydrates. We understand quite a lot about ice, but probably still need a lot more. But one thing we didn't understand was what some of these potential evaporite materials were. And we had another bit of a clue in that when Cassini first arrived at Saturn, it actually launched a small probe, the Huygens probe, which landed well, floated down and splodged on the surface. They actually had a little probe on the bottom of it that was meant to work out if the surface of Titan was solid, liquid, or splodgy, and it was slightly undeterminate. But one of the things it did note was there was benzene on the surface. So a group at the Jet Propulsion Laboratory of NASA started exploring, is there a way that benzene could form a solid under Titan conditions? And I should say, you thought it was cold in Canberra. A sunny day on Titan is around 90 Kelvin. And so you freeze benzene, and you see benzene has that wonderful platy crystals, and I should say this is... and when you introduce liquid ethane, ethane doesn't actually freeze to 89 Kelvin. And there's actually that nice thought that ethane, because it doesn't freeze till 89 Kelvin, it's almost going to be like water on the surface of Earth, because we're around 0. We have ice and liquid. You can have both frozen ethane and liquid ethane on the surface of Titan. So that's a really nice analogy there as well. But you can see that there was quite a dramatic transformation in those crystals. They all broke up, and they used Raman spectroscopy to be able to actually see, hang on, there's something different about the crystal arrangement. So interestingly, this was a capability that the Jet Propulsion Laboratory didn't have to do crystal structure solutions, so they came to Australian synchrotron to do, which is always nice to fill a gap of NASA. And we undertook a diffraction experiment on this material, and so we recreated the same thing. So there's the sample at 170 Kelvin. In fact, that's the point where we've just frozen the benzene in the capillary tube. And then we've cooled it down to 90 Kelvin, and then we've introduced liquid ethane. And it's undergone this transition, and beautifully we have all these brand new diffraction peaks appearing there. And really nicely is that one at lower angles there, which suggests that the unit cell is bigger than benzene. And then here we go, and we hark all the way back to Lonsdale's work of that flat benzene molecule. And we're able to actually solve the structure and see that it's actually got a tunnel structure. Thanks, Professor Pring, for introducing that concept. That the benzene rings sort of expand a little bit, and they're held together by their sort of conventional interactions, the hydrogen pi bonding. But they leave a channel, and in that channel you actually get the ethane molecules sitting in. Now, the really exciting thing about this, and this is why we're sort of beginning to think of icy mineralogy, is that there are other small linear molecules on the surface in that vicinity, things like hydrogen cyanide and acetylene. They could very easily sit in that hole as well. And so we get the idea of, just like terrestrial mineralogy, of replacement, of materials being able to move between these materials as well. But also gives it a nice mechanism to evaporate out of. So it's a very nice evaporate structure. So that we've just recently submitted for review. So I've talked about the terrestrial planets, and I've talked about the icy moons. I've obviously missed out quite a big class of planet, a very big class of planet in our solar system, and that's some of the gas giants. And so I thought I would tell you a bit of a story about Uranus. Most people tend to talk about Jupiter or Saturn, and sometimes Neptune, and I think Uranus sometimes gets a little bit maligned. Uranus is fantastically interesting, and it's a slightly strange planet. It rotates the wrong way. It's like it's had a sort of hard night, and it's flopped back on its surface, and it rotates in a very different way to the other planets in the solar system. But then also, it has a very strange magnetic field, and I should say that this is a property it shares with Neptune as well, where its magnetic field, unlike ours on Earth, is not centered around our core. It's actually centered to one side, and is at great big angle to its rotation axis as well. Now, one of the theories as to why that is because the magnetic field isn't being generated in the core. It's been generated in the large icy mantle, which it's thought to make up most of the planet there. And that's a great big volume of the planet that is mainly made, we think, of water, ammonia, and methane at quite horrendous pressures and temperatures. Now, I should say there was some... we're sort of just starting to pose these questions and do these experiments into the gas giants. And one interesting thing is we noticed there wasn't enough xenon as Voyager went past in the gaseous envelope. So where has all the xenon gone? And what we can do now, and crystallography is absolutely key to understanding materials under extreme conditions, because you can get X-rays in and you can get diffraction out. We recreate these extreme conditions using a diamond anvil cell. A diamond anvil cell is pretty developed technology now. And so for this particular experiment, we loaded water and xenon and a little piece of platinum there to absorb the sample. And just for the audience here, you can see an example of how big a diamond anvil cell is. A very powerful instrument that sits in the palm of your hand. And you can see how small the samples are. There's my little finger for scale up at the top there. So very, very tiny samples, very strong materials, the diamonds, which are also great because you can see through them. You can use the microscope to see what your sample's doing. So this was an experiment we undertook at the ESRF at ID27, and we compressed the sample to 50 gigapascals. And then you can see, as we're warming up with the laser, you can see the xenon sat there in the powder pattern, you can see the platinum, you can see the high-pressure ice. So that's our starting materials. But then when we get to the 1600 Kelvin with the laser, we get to the point where we're in the icy mantle conditions of Uranus. We get, bam, a really interesting phase transition. And that's a material that is it's a reaction product between xenon and water. And unfortunately, from that data, we couldn't actually solve the structure. We used molecular dynamics as well to work on that structure. So that's a really, really nice example of where crystallography can probe those conditions, which, and I'm sure you'll hear a bit more about this later, that other techniques can't necessarily go. And so with that, I thought I would move a little bit to the future and just wrap up my presentation. And although I said I've covered the terrestrial planets, the icy moons, and the gas giants, I've missed out the dwarf planets. And that's because we are just on the cusp of knowing more about this. This is a picture taken a couple of months ago by New Horizons, which is going to arrive at Pluto in less than 50 days. And we can already see potential differences on the surface and an icy crust there. And so with that, I'll acknowledge the people that have contributed to this presentation. And thank you so much for listening.
Thank you, Helen, for a lovely lecture. Time for questions. Yes, yeah.
Ian McDougall, ANU. Why, with the volcanic activity on Titan, doesn't the hydrocarbons explode? Is it the lack of oxygen or what?
Absolutely, lack of oxygen. And also, we've actually not seen anything, I should say, we've not seen anything active. At the moment, we've seen remnants of volcanic activity, or what we interpret to be volcanic activity. We've yet to do, and Cassini is trying to do this, take pictures, and there are teams of people looking at a picture taken 3 years ago and a picture taken this year to see if there's any differences. But as yet, there's been some evidence of a thermal signature on Titan, but as yet, we've yet to see, people are playing a very sophisticated game of spot the difference, but we've yet to see any activity. So it could be that it's not so active, but yes, the lack of oxygen is the chief reason there.
Right. What are the arrangements for getting samples? How do you manage that?
Well, the great thing about Europa is it looks like it's quite a simple composition. So we just base on the chemistry we get from the spectroscopy. We've yet to even get, apart from meteorites, which are sort of auto-sample return from Mars, we've yet to actually even go to Mars and dig up a bit. And I think that's one of the next stages that NASA are going to undertake. So with the isomoons, it is that they're dominated by very, very simple materials, but simple materials under strange conditions that we still don't understand enough about.
Right, final question.
Oh.
Yes, Rob Robinson from ANSTO. One of these things, when we were testifying for NCRIS, some time ago, and started to think about, well, what were the grand challenges that Australia might participate in? I think one of the things we should think about with these facilities is that when rocks do come back from Mars, we should be good enough that we're in the scrum to study them. And we've actually got another person at ANSTO who, earlier in her career, looked at moon rocks in Germany for NASA when they came back. So I think, one of the hopes in the future would be that when you know, rocks do come back from Mars, we can play in that space.
ANSTO's the place to be. Well, on that note, and thanks again to ANSTO and all the speakers this morning, would you please join me in thanking them for a superb contribution.